Hello mathematicians, welcome to our new topic, numbers and functions. It's a big topic, as with every topic, it's an important topic, but as with algebra, it's a lot of building block work for later topics. Okay, so our first little bit is to do with recurring decimals. There's a fair bit of background to this, we won't cover all of it, but just to put things that you already know into perspective. First of all, we know that fractions can be written as decimals, and if they're decimals which are precise, or come to a stop, then they're called terminating decimals. And we do that simply by doing what the fraction says. We divide 1 by 4. If we stuck it into the calculator, we get 0.25. If we are given a decimal and we want to recover the fraction, then we use, again, a similar concept just based on our place values. We divide by the appropriate power of 10. So if I had 0.25, for example, I know that I've got 2 tenths and 5 hundredths. If I add those together by getting a common denominator, that gives me 25 hundredths. And if I cancel that down, that gives me my original quarter. Now, any numbers that we can write as a fraction which terminates are called rational numbers. It's not going to make much difference to us whether we get that or not, but it's just another maths term. Numbers which can't be written as terminating decimals are usually referred to as irrationals, and our calculator does an approximation of that. So in a question, as you will have encountered in the first topic, where it says find the exact value, what we end up doing is leaving things in a certain form. So we write pi as the symbol pi, for example. We write surds like root 3 as root 3 because the calculator can only give an approximation. There's a sort of a halfway house, if you like, which is a recurring decimal. And a recurring decimal, while it doesn't terminate, it goes on and on and on, we can actually write it as an exact fraction. And we can recover what that exact fraction is by a few different methods. So this is the first one that we'll have a look at. So if we had, for example, the recurring decimal 0.3 repeater, we know that the dot means that 3 repeats infinitely. So if we say let n equal that thing with the 3 going on forever, what we can do is then take 10 times n. So it shifts the decimal point one place to the right. When we do that, we get, again, a tail that goes on and on forever, but it's exactly the same as this bit here. And now, it's a little like simultaneous equations. We don't number them, but we can think of them as equation 1 and 2, and we subtract 1 from 2. So n from 10n gives us 9n, and our 3.3 going on forever minus our 0.3 going on forever gives us exactly 3. So then n equals exactly 3 on 9, and it equals exactly 1/3. Now there are little tricks to do with how we set these two lines up, and it's covered in this little quotation over here. We multiply by the number of places to the start of the recurring portion, and then by the number of places to the end of the recurring portion. So up here, we multiplied by 10 to take us to the end of the recurring portion. And then we subtract the two equations. So let's have a look at these in practice. So if we have 0.7 repeater, then our recurring portion is right at the start. So let n equal 0.777 going on and on. If we multiply it by 10, that will take us to the end of the recurring portion, so 7.777. Take the first from the second line, so that gives us 9n equals 7, so n equals 7/9 as the exact fraction representing that terminating decimal. 0.45 on the other hand, if we let n equal this, we've got 454545 going on and on forever. So one place takes us, that's a point, one place takes us to the start of the recurring decimal, so that's our 1 just here. And then we'd have to multiply by 100 to shift that decimal point 2 places to the right, so that we've covered the recurring section. And now, when we subtract, we'll get 99n equals 45 point all of that stuff minus all of that stuff, so we get 45. So n is 45 on 99. For our next example, if n equals 0.26 repeater, then we've got this. So we need to get to the start of the terminating section, so we multiply by 10 and we'll get 2.666. And then if we multiply by 100, our original by 100, that will take us to 26.666. So when we do this subtraction, that will give us that 90n is 26.66 minus 2.66, which will be exactly 24. So n is 24 on 90, which of course cancels down then to 12 on 45, which cancels further to 4 on 15. And our last example, 2.102, if n equals that thing, 2.102, then it's 102, 102, 102, etc. So what do we have to do? Well, 1n will take us to the start of the recurring bit. To get to the end of the recurring bit, we need 1000 n. So that will give us 2102.102102 forever. So subtract 999n equals 2102 and that bit minus 2 and that bit, so it gives us 2100. So n is 2100 on 999. That's as an improper fraction, or I could have just focused on 2 and that bit, which would give us something else. So you could have a go at these couple in 2a.